So let's get started on time. Don't want the other presentations to be late, right? Well, my name is Thadeu. I work on the LTC at IBM, and I'm here to talk about DMA API and how it performs on IOMMU environments. Since this is the Collaboration Summit, I would like some input if I'm going to a dead end or there are some trade-offs here. So probably some people may tell me how we should proceed in that. Okay, so there is some bias towards PowerPC 64, the P series at IBM. Well, I tried to take a look at the other platforms. The tests I ran are mostly on the PowerPC, but I believe that some of the results would be similar, and I'll try to tell you why. And please help me share anything you want about the other platforms. So I'll tell you about why I'm doing this, what's the use of this. I'll tell you what this is about or what technologies are involved in this. How much is how bad or how good it performs depending on the algorithm we are using, and how we should proceed, some of the suggestions about trying to move forward. So the why is, if we want to do I/O virtualization with good performance, we usually want to do some form of PCI pass-through. That's one of the ways of doing it. And one of the things that PCI pass-through provides us is isolation between gas. So we want to give the card to one gas without affecting other gas. And we want good performance. We may get some stability, mainly when we use IOMMUs, and it somehow helps us debug things. So I'll try to get into more detail about the stability and debug stuff. So on the PowerPC, when a PCI card tries to do an access to the DMA region, it should not supposed to. We get an error, and we can handle that. We can try to recover from that, and well, system doesn't crash, or it's not supposed to, or we don't write to the memory where the card is not supposed to write, so we are not overwriting stuff. So one of the other things it help us with is debugging buggy drivers. So most of the time we see this stuff happens, it's because of the drivers, not because of the card. So it has helped us a lot to detect some bugs and try to fix them. Well, of course, there's the issue of security, and we don't want our new Thunderbolt cards trying to access our memory and reading our passwords and stuff like that. So the two things that are involved here is the DMA API. Right now we have the streaming DMA API, which allows us to, in the driver, give a virtual address and get an IO address, a DMA address we can send to the card. So in most platforms, this is straightforward. We just translate the virtual address to physical address. That's the same address that is going through the bus. So this is a very cheap, if not free, operation. So in other cases, we might have an IOMMU, or we might have to do some cache flushing or stuff like that to allow coherence. And when we have an IOMMU, what we do have to do is insert an entry into the IOMMU table and use that. But in order to do that, we have to allocate an address. We can't share addresses between different virtual addresses. So that's the biggest problem that I'm trying to solve here. So the IOMMU protects us from the access. So if a PCI card sends a DMA access or read or write, and it doesn't have a translation, well, it's not going to get access to that memory. So we must put that addresses in there. So in the PowerPC platform, this is done through a form of power virtualization, IOMMU. So the guest sends to the host a request to insert that entry into the table. And we do that for every DMA map call. KVM PVDMA didn't make into mainline. It's something that some patches were sent about in 2008, and since that, nobody ever pushed that forward anymore. So I'm not sure if there's anybody planning on doing that. So is he still working on it? I haven't seen any patches past 2008.
I know that they are trying to integrate it with KVM, the IOMMU. That's for sure. And I'm pretty sure he did some work on IOMMU.
Yes, there is IOMMU supporting KVM, and what it does is map the entire guest. So that's one of the trade-offs I was talking about. Yeah. So you have to ping the whole memory. So that's one of the trade-offs we are doing here. We cannot do overcommit, and so I'm not sure if that's really a problem.
But isn't that the case with any IOMMU, that you have to pin the...
You have to, but you don't have to pin all the guest memory if you're doing paravirtualized DMA, because then the guest requests the host to.
Oh, yeah. Yeah, you're right.
So not sure if anybody's interested in doing that. So that's one of the inputs that I was looking to. So that's the whole advantage of PVDMA. Okay, so well, one of the other reasons you might want to use a PVDMA is because you don't want to have, if you have too much memory that you need to map, you'll need a very huge, not huge, but you need a bigger table for the mappings. So that's going to be a memory overhead in there. So if we have a direct mapping like that, so we map the whole guest memory before we start the guest, the only thing the guest has to do is adding an offset. In fact, it's just doing the virtual guest physical translation. So it's just what it needs to do. And while mapping, it has to do nothing at all. But when we do some kind of power virtualized DMA, we have to allocate the IO virtual address and then insert the mapping to the IOMMU. And when we unmap, we have to remove that mapping and release that allocation. So the performance for PVDMA involves a hypercall cost or something similar, and the IO via allocation cost. And that's where we have some contention. So if we have too many threads trying to do that allocation, well, it may have some problems, and I'll try to show that. Everything okay? Okay, so from a driver perspective, you don't want to do too many calls to the DMA map API because of that issue, because of that performance issue. So if you can avoid it somehow, well, you're probably going to improve your performance. So we had a 10 gigabits NIC driver, which called the DMA map for every packet it received. And it fragmented the packet in different rings. So in fact, for every packet, we could potentially call the DMA map 3 or 4 times. And the performance of that was about 3 gigabits per second in a 10 gigabits card. So it was pretty awful. So we did some driver optimization, and what we did was mapping the whole pages that chunk allocator that the driver already had used. So we mapped the whole pages, and we just had to solve the problem that when to unmap those pages. So that's the only problem we had to solve. It was not trivial, but was doable. And the result is 9.5 gigabits per second. So you have to take care when you do that in the driver, because otherwise you may have very bad performance. The other solution is trying to solve the DMA map API itself. So for some drivers, optimization has already been done, or we don't want to do too much work on every driver, so it's possible that we can just fix it once. So, and it's still, this performance we can achieve while using TSO. So if we drop TSO and use UDP, for example, we are just doing 6 to 7 gigabits per second. And if we drop TSO and use just GSO for TCP, we get about the same performance, so 6 to 7 gigabits per second. So that's not really good. And we are going to have 40 gigabits per second NICs in the future, so, and not so distant future. Okay, so from now on, I'm going to show you some results of some tests I made. I'm going to describe you those tests. So what I did was, these are not tested with a real driver. So I had a very simple driver which only did a call to the DMA map API 1,000,000 times. So what I did was I called the DMA map 1,000 times, then 1,000 times the DMA unmap, and then I repeated that 1,000 times. Okay, so I had about 1,000 mappings at once, and then I repeated that 1,000 times. These are some comparatively results. I'll break them up later and see how we can analyze this. But basically, this one is the red-black tree used by Intel. So I ported it to Power, and I was very naive thinking, oh, a tree should be very nice to do that. And well, in fact, it was not what I expected was the worst performance that we had. So the code we had about a year ago on Power is this green line. It's basically a bitmap. So we try to find in the bitmap whatever a sequence of bits that allows us to map the number of pages we need. So it's just a bitmap find free area or something like that. And we take a lock, do that allocation, insert the entries in the IOMMU table, and then release the lock. So in the entire time, what we are doing is we are holding a lock and not allowing any other CPU to do that same operation. So if you want to handle a packet, you got to wait for the other CPU to handle the other packet. So we see this performance here. So I'll go into detail later. So the code we have right now, what it does is that it uses bitmap pools. So instead of holding a single lock for the entire pool, for the entire bitmap, the CPU, the current CPU uses to index a pool. So we hold a lock for that single pool, and the other CPU can use another pool to try to allocate memory. So it's much better. And those other ones are basically direct access. It grows a little because I'm using more threads than cores, so we still have some serialization. So in order to see if the IOMMU itself, because it's virtualized, so the hypervisor is doing something, in order to see if the hypervisor is doing any contention, I tested only doing direct access to the IOMMU, so I skipped the DMA API. So I'm not doing any access to the real DMA API here. I'm just calling the insert entry in the table and remove the entry into the table. And I just added an address for every iteration. And this is a system with 16 cores, but I was running on a partition that had about 11 cores dedicated to it. So what we have here is that until we get to that many cores that we have, we can still do 1 million operations in about 0.6 seconds, 0.7 seconds. And if we have 4 threads, we are doing 4 million operations in that same time. So it's all parallelized, okay? But as we add more threads than we have cores, well, we need to do some serialization and take more time to do that. But there's no problem in the IOMMU itself. So if I put more cores, I can use more threads. So on power, we can still try to map the entire guest when we have just booted, or in fact, when we probe the device, we do a call to the DMA SAT Mask, and underlying, if we can request a DMA window large enough to map the whole memory, we do it, and now we can just add an offset and follow that procedure I described here. So just add an offset while mapping, and unmapping does almost nothing. So in that case, we have same behavior, but the difference here is that it takes much less time. We are just adding a number, so just the we are measuring here how much number crunch your processor can do. But we still, until 8 cores, no problem. After that, something like growing linearly. I just put that number for 1024 threads because that's, well, not really nice, but I believe that's maybe something related to the scheduler. We're scheduling here 2024 threads, so maybe it doesn't perform that well because of that. So I did some hacking, and the DMA window we have usually by default, it's a 2 gigabytes window. So what I did was set the memory for the partition for 2 gigabytes. So I ensure that I can map the whole memory, but still I'm going to do those IOMMU insertions every time I call the DMA API. So I want to see if adding those two, I get the same behavior. So we should get. I didn't expect anything different from that. Luckily, I didn't get. I would have to explain to you why that happened. So it's nothing more than adding those two graphics. So it's very similar to this one, right? So this is what we had on Power. And although I told you that I would be biased somehow, the code on mainframe and on Spark are just the same. Okay, so they take a lock, they do the IOMMU work, and they allocate memory from a bitmap, they do the IOMMU work, and then they release the lock. So now for 2 threads, it takes me more than twice the time, or about twice the time. And for 4 threads, more than 4 times takes to do 1 million operations with one single thread. And things get a lot worse when you get 64 threads. So that's not good. And that explains a lot about the results of that card I showed you before. So can we improve that? Or how should we improve that? Is there any allocation algorithm that we can use? And we know that the problem is not the IOMMU itself, right? The problem should be somewhere else, and it is in the bitmap allocation. So Anton Blanchard, who works on the LTC, has sent some patches in which he did 2 things. We don't need to take the lock to do the IOMMU insertion. If we already have an address, we don't need to hold that lock. So we just take the lock to do the bitmap allocation, and that has improved about 30% for the throughput of a card he tested. And after that, he did the bitmap pool work. So he uses 4 pools unless the window is not that big, I guess. I don't remember the details. So unless it's not that big, he uses one single pool. But for the default, the default window we have, he used 4 pools. So we see that about at 4 threads, we have the same performance as a single thread. After that, we start growing. So perhaps we should try to use as many pools as cores, and at least that problem is solved. Okay, so that's one possible improvement. I didn't get the chance to try it. Sorry. So I started looking at other architectures implementations, and I noticed that the Intel IOMMU was using our red-black tree for that allocation, and I thought that could be a good idea. So I ported that to Power and ran those tests. At first, I tested it with the card itself, not my driver, simple driver. So it kind of worked. I could use ping, but when I tried to run a TCP string that tried to send a lot of things, the system just stopped working. I didn't know why, so I guessed my port was too quick and it wasn't working. So I I had already fixed 2 bugs on that port, so must be something wrong that I did, right? So then I decided to test with that driver, and you may notice that the other graphics have 256 threads, 64 threads. This one, for example, ran for about 2 minutes, or maybe longer, 5, 7 minutes. I may have the original numbers with me. But with 8 threads, it took about, well, I guess it was about 7, 8 minutes, and I had to take a coffee and wait for that, and the system was not responding. In fact, you have those stuck threads debugging going through the log, so there is some stuck thread here, the kernel says to me, so is that a bug? We have a stack trace and stuff like that, but no, it's just that the system call is not returning, it's waiting for too long, and well, I didn't dare run it for 16 threads because the growth also is not that good. So for a single thread, we get about 7 seconds, and it, I believe this was about 50 seconds, 40, 50 seconds. So I believe that for 16 threads, it would not take only 15 minutes, or maybe take half an hour, don't know. So since this code runs originally on Intel, I asked a friend to give me access to one of those machines, and then I just ported the driver to another PCI IG and ran the same thing on there. So to be fair, it seems to work better. Not sure how many cores this system have, but it works better. There is a caching that the original algorithm uses and that I don't use on Power, so may make a difference. So, but it still grows a lot, and for 8 threads, I still take 2 minutes, so it's too long. So I believe there's a lot of potential to improve here, and in this case, I didn't have to run any guest. I just have to activate the IOMMU, which you want to do if you have any Express or Thunderbolt port on your notebook. You should be doing it. So if you have an Express port or an Express card or Thunderbolt port and you want to run a NIC, you don't want to, well, you want to use it for the security, but you don't want to use it because of the performance. So that's something we got to fix. So any questions here? Those are the tests I ran. I still want to do more testing with other algorithms. There is the JanaLock, which is used to try to allocate a range. It does exactly what this code does. It reserves some memory space. It does not allocate memory itself, but a memory address space, and it uses a bitmap. And since I fixed the bug in there, I remembered that it was a simple bitmap and used spin lock, just the same. So I didn't think it was worth it, but then today I look at it again, and there was some improvement in there, and they tried to do a lockless allocation using RCU. So maybe we could try that and see how that works. So one of the things that many chips now are shipping with IOMMUs, and we have a drivers IOMMU directory where we have lots of drivers, and they're not all exploiting the DMA API, so they're not really coupled. And when people use KVM, what they do is just map a physical address with a guest an I/O address with a guest physical address, and so they don't have to do any allocation. They just run through those addresses and insert those into the IOMMU, and they do that for the whole gas memory. So they're not really hooking into the DMA API. For the KVM case where it maps the whole gas memory, it makes sense. But if we want to use that on the host, we must hook that into the DMA API somehow. Or we just map the whole system memory, which might not be a too good idea. And one of the things that I'm worried about is about boot time. So when we're booting, if we have to insert those IOMMU entries to the whole gas memory or the whole system memory, we may delay some of the boot time. So something that we might want to improve. But well, I would also like to bring those IOMMU support in those old architectures that have it into the IOMMU drivers infrastructure and see how can we use that. So better allocation algorithms and sharing allocation algorithms. So right now, the improvement that went into Power could go into Spark and S390. So it's not in there, so that's potential to do that. And we probably shouldn't have code copied over the architecture. They should really share them. And if we ever do the PVDMA on KVM, well, that's some work that could already fix any performance issues that we would see if we ever did that. So one other possible thing is trying another tree-based algorithms. I'm not sure if Radix tree would work, or maybe it's something similar to what we do in the IDR, IDA. Not sure if that's going to work, but that's something we could look into and see if that goes well. So, well, I went too fast, I guess. But, some of the conclusions is that we have a lower bound for the allocation algorithms, which is when we just do the IOMMU work. So that's a lower bound. If we ever have an algorithm that performs just like this one, it means that we did our job right. So I believe that this is something that we should try to do, try to get into this, because that's what we have right now. And the problem is worse when we grow. I didn't try it on a system with 256 cores. I'm not sure how that's going to work, but I believe that's going to be pretty nasty if we are between those lines. Well, one of the other conclusion is that the current arbitrary code that Intel IOMMU uses is not that good. Well, in fact, it's really bad. It's crappy code. So, I tried running only, so I did that 1 million insertion to the IOMMU, and then I repeated that. Then I thought, maybe we are trying to do because the code tries to allocate from a K-man cache for the arbitrary nodes. So maybe you're trashing the system, maybe something going wrong here. So let me try being nice and just doing 10 allocations, 10 maps, 10 maps, and do that 100,000 times. It's still 1 million operations, but we do not have 1,000, which is not that much because our NIC drivers have large rings. Maybe we are going to reduce that in the buffer bloat work, but still for the receive query, we might want to keep that, and we might still have many in-flight I/O. So, well, that didn't fix it. It was a huge improvement. I didn't make a graphic to show that, but it still grew a lot, but was not that bad. But not sure if that shows it's not a problem. I don't believe. I believe this is a problem, and that we can try to use the bitmap allocation on Intel. I didn't have time to try that. One issue that it might have is that we now have to have a DMA window large enough. Not sure if the Intel code limits that to the 32-bit DMA window. If it does, it makes things easier. But if it doesn't, we will have to allocate memory for that bitmap. And I didn't see too much IOMMU use outside of the Power platform and the other large servers platform. I see that some of the chips for ARM are using it, but I'm not sure they're really well exploited. Maybe I'm wrong, but I didn't see, at least in mainline, I didn't see too many calls into that API. So we don't have DMA API calling into that. We have KVM calling into that, but that's it. And sometimes we have some very specific drivers calling into that. So it seems that some chip guys are just doing the IOMMU for a single driver. So maybe we should try to exploit that more. But certainly in our laptops, we are not using it. And there are not many laptops supporting it right now, but the Intel chip does, but the BIOS is crap, so it does not support it. This is it. Any questions or any suggestions on how we should move forward?
Underuse is...
Does it work now? Oh, it does. So, underused is, you can't really agree with it, because the primarily user of that IOMMU interface is in fact KVM. I mean, that's where it came from, why this whole thing was implemented the way it was, so that KVM could use it. Because prior to that, they had their own implementation. They had a separate fork actually for KVM, so that they can do device assignment. The whole idea of the IOMMU stuff is that you can do device assignment in a generic way. So if you're not doing device assignment, chances you wouldn't need IOMMUs. And the only way currently you can do device assignment is basically using KVM for Xen. I'm not sure, I can't really talk for Xen. But then, as Xen is using its own hypervisor, chances that I have a different infrastructure for doing device assignment. I can't really talk for Xen here, so I don't really know it in that depth. And so I'm not surprised that there's only one user in the kernel code, namely KVM, because it was made for KVM. But other than that, on the KVM side, it works really neat and really nicely. With the said IOMMU overhead you just mentioned, but yes, this was about to be expected. And I'm not quite sure whether the overhead is just due to the code, meaning the kernel side, but not only, also the firmware/hardware implementation also said IOMMU, which also might have a performance impact, as you need to do the translation in firmware.
Yeah, well, in that case, this is a performance issue on the guest, on the operation system. As I showed, when we just do the IOMMU insertion, we have very nice graphic. So as long as we are doing as much threads as we have cores, we can still do 1 million operations per core at the same time. So it's still not that great. We have to do a hypercall, and you see that when we don't have to do that, we can do 1 million operations in about 20 milliseconds, and we take 30, 40 times that when we do the IOMMU insertions. But still, it's scalable. We can do as much threads as we have cores. And the other thing, do we want to do IOMMU only with KVM and only with virtualization? Don't we want to do that when we are doing that on the host? Do we trust our devices that much? As I said, one of the things that it gives us is some stability and gives us some way of debugging it. Any device driver bug will not allow the device to write into the memory, and any device bug or any device security issue will not allow it to read or write the whole system memory. So that's one of the other things you get from it. So not sure if that's should we go to that? Should we invest that much time trying to improve performance for just that, or is that really important? And for the virtualization stuff, do we want to ping the whole gas memory, or do we want to allow PCI pass-through device assignment at the same time allow some overcommit?
We definitely want to map individual bits of their own IOMMU. The main problem is, in fact, that you currently have to pin the entire guest if you're using IOMMUs. And this is also the main reason why something like SRLB or so is being steadfastly rejected by the KVM community, because as you have to pin the memory, you can't migrate it, which is the main bone of contention. And everyone and the dog is claiming, you have to migrate, you have to migrate. I still don't quite subscribe to that one, but that's just me. So yes, we definitely want to make the IOMMU more fine-grained. Ideally, having the IOMMU set up on request. So whenever we do, we only will be set. So ideally, we will be setting up the IOMMU once we issue a request and delete the mapping after we finish with that request. Because then we can easily migrate. That won't be a problem. We just pin the memory for the request, which we have to wait for anyway. So that would be, in an ideal world, that's what we would be doing. However, given some hardware limitations, this probably won't be possible. But yes, we do want to have it more fine-grained.
Is there any hardware limitations that Intel IOMMU limitation or?
No, but on PowerPC?
Not really. We do that.
Well, on PowerPC you can map only PCI ranges. You cannot map individual PCI device, but rather PCI ranges. So everything which is within that range will be mapped automatically, whether you want it or not.
What do you mean by PCI ranges?
Well, the IOVA you were talking about is not just a single PCI device, but rather...
Oh, the partitionable...
It's the partition of range. So
okay.
Whenever you issue a call on PCIers, you will be mapping everything which is in that region, whatever that is, without whether you want it or not. So you can restrict it to individual devices.
I guess that's also a limitation in other IOMMUs. If you have, for example, PCI-X devices behind a PCI Express bridge, you have to map all those PCI-X X devices will have access to that same mapping.
Yes, you would. But then the classical use case for IOMMUs is in fact SIRV. So that you have a physical device which is spread out into several virtual devices, and each of those virtual devices is mapped to a different guest. That's the classical usage scenario here. And SIRV only works for PCI Express, so that point is pretty much moot. And also that I doubt that you'll be getting much PCI devices or even PCI-X devices in current servers.
Sure, but does that limitation not apply for PCI SROV functions as well? So
there are, as to my knowledge, all SRV part implementations currently are PCI Express.
sure, but I mean, yeah, but I mean, doesn't that IOMMU limitation not apply for the PCI physical function, or does it apply for the P series and not apply for Intel? Is that what you're saying?
For Intel, you can map individual PCI devices. Actually, for Intel, the index into the lookup table is the PCI device. Something like so. Yes, you map individual devices because you don't really because the PCI enumeration is somewhat shifty, and you might have you only have the PCI bus as the instance atop of which. So no, for Intel you can just map individual devices.
So any comments, inputs, any more? Well, this is it. Thank you.